when a charged particle moves through a magnetic field at some speed v, we know that the force experienced on that charged particle is always perpendicular to the direction of the velocity. So what happens is the magnetic force cannot speed up or slow down a charged particle, a moving charged particle, but it can change that particle's direction. So two things come about. If the velocity is exactly perpendicular to the magnetic field, then the path of the particle will be a circular path. So for example, let's imagine a particle that's going in this direction. The magnetic field is coming at you, right? So V cross B, the force will be downward. So what would happen is the particle will go in a circle like this. Now, if some component of the magnetic field, some component of the velocity is not perpendicular to the magnetic field, what will happen is the component of the velocity that's parallel to the magnetic field won't change. Only the component of the velocity that's perpendicular to the magnetic field will change. So rather than a circular orbit like this, you'll get what's called a helical orbit, where the magnet object will come towards you, or the object will move away from you. Think of a slinky, and the winding, constant cylinder of a slinky. That's the path that a charged particle will make if it has some component of the velocity parallel to the magnetic field. Now, your book uses the word spiral here. That is not accurate. I don't know why they do that. A spiral is this, where an object moves out or moves in, spiraling inward or outward. A helical path is constant in radius. So a circular path, a particle will move along in a circle, right? In a circle. For a helical path, the circle stays the same. It's just that the particle either spins out at you or spins into the board. It still stays at the same circular radius. So again, a slinky is probably the most obvious example. Or for those of you in biology, a DNA, right? A DNA is a double helix molecule, where you have two interspiraling molecules going around one another. It's like take a zipper and twist it. So it's a helical path, not a spiral path. Again, I don't know why your book uses spiral. That's not accurate. Now, if the particle's motion is completely perpendicular to the magnetic field, then theta, which is the angle measured between the velocity and the magnetic field, is 90 degrees, right? That's what perpendicular means. If theta is 90 degrees, sine of 90 degrees is equal to 1. So the magnetic force equation reduces down to this. Normally there's a sine theta at the end of that, but we just said we're going to assume theta is 90 degrees, so we get this equation. This equation only works if the velocity and the magnetic field are exactly perpendicular. Always use the previous, more explicit, more complete version of the equation for your homework problems. Now, since the force is always perpendicular to the velocity in this case, the particle undergoes what's called uniform circular motion. And we talked about that last semester in Physics 141. So again, you have some central object, you have some force, some centripetal force inward, which causes, of course, a centripetal acceleration. That is perpendicular to the velocity of the particle at all points. So wherever the particle is, the acceleration is always inward and the velocity is always perpendicular to that acceleration. So the magnitude of the velocity doesn't change. The speed doesn't change, but the direction does. And as I said in previous videos, it's as if the magnetic force doesn't have a gas pedal or a brake. It can't slow down or speed up the particle, but it can turn it. It does have a steering wheel. It does turn it in different directions. So the equation for centripetal force, going back to last semester, is mass times the centripetal acceleration, which is v squared over r. We have the equation for magnetic force, but this magnetic force acts as a centripetal force. Remember, centripetal force is just a category of force. It's any force that acts inward. For the Moon-Earth system, gravity is a centripetal force. If I put a rope around a bucket and swing that bucket around my head, the tension in the rope is the centripetal force. In this case, the magnetic field acts as a centripetal force. So I can set these two equations equal to one another. And you can see that I want to know, what is the radius here? How big a circle is that particle going to make? Is it going to make a tiny circle, a rapidly moving circle, or is it going to make a very big circle as it moves through space? Well, to figure out how big that radius is, it depends on the mass of the particle. So the more massive the particle is, the bigger the radius is. It depends on how fast that particle is moving. So the faster the particle is moving, the bigger the radius. It's inversely proportional to the charge of the particle. So the more charge the particle has, the smaller the radius is going to be, and how strong the magnetic field is. Again, the strength of the magnetic field, think of it as how much you can turn that steering wheel. So a strong magnetic field has the steering wheel turned a lot, so you make a very small radius turn. A weak magnetic field only has the steering wheel turned a little bit, so you make a larger radius turn. So R here is the radius of the circular path of a particle that has mass m, so you need to know the mass of a particle to know the radius. Charge q, you need to know how much charge is on that particle. If the particle has no mass, there's no radius. If the particle has no charge, the radius is infinitely large. Effectively, remember, magnetic forces can only affect moving charged particles. If the charge is zero or the velocity is zero, the particle doesn't move. There is no radius that the particle spins around because the particle doesn't feel a force from the magnetic field. And then finally, of a particle mass m and charge q moving at speed v in a magnetic field of strength B. So if you know the mass of the particle, the speed of the particle, the charge on the particle, and how strong the magnetic field is, and we make this assumption, remember, that the velocity of the magnetic field are perpendicular to one another, you can calculate the radius. What if the velocity and the magnetic field aren't perpendicular to each other? What if you have this helical motion and you want to calculate the radius of the helix? You can still do that. You just have to use the appropriate sign, the angle. You can't just assume that it's 90 degrees. You have to go back to this original equation that had that sine theta on the end of it and put in that angle. Or another way of thinking about it is look at the velocity component of the velocity that's perpendicular to the magnetic field. Little upside down T meaning perpendicular, right angles. So there's some component of the velocity that's with the magnetic field, some component that's perpendicular. So for example, if we have our magnetic field here going to the right, and let's say the velocity of the particle is like this. Well, then there's some component of that velocity, v parallel to the magnetic field, that we don't need to worry about, and then there's some component v perpendicular that we do want to worry about. So you can just use trigonometry to figure out what is the perpendicular velocity, plug that perpendicular velocity in here, and figure out what the radius is of the helical path. Because this parallel velocity, this particle then will spin like this, moving along the magnetic field line. You can sort of think of it as being caught in the magnetic field line, wrapping around it, moving around it in a helical pattern. Now, this has practical applications, and we'll talk about those in just a moment. When charged particles approach a magnetic field line, they can, if they're going fast enough, pass across the magnetic field lines, and their velocity is altered, but they can escape. Or they can get trapped into helical orbits around the magnetic field lines rather than crossing them. Now, the Earth has a magnetic field, right? So we have planet Earth here, north and south magnetic pole. And there are magnetic field lines. I'm just going to draw the ones around the Earth. and they go through the Earth as well. They don't stop or start. They actually pass through. And they don't cross. Those magnetic field lines exist around the Earth, and they protect the Earth. It's fortunate we're there because the Earth experiences what's called a solar wind. This solar wind is comprised of charged particles from the sun. Now, most of these charged particles hit the Earth's magnetic field and get blown around and away from the Earth. That's great. However, some of them get trapped and start to do helical orbits around the Earth's magnetic field, and they follow those magnetic lines, and they crash into Earth's atmosphere at the north magnetic and south magnetic poles, or near those poles. Now, when these charged particles crash into the upper atmosphere, we experience this as aurora. So the aurora borealis in the north and the aurora australis in the south, the beautiful lights in the sky that you see at extremely northern and southern latitudes, is due to the solar wind being captured by these magnetic field lines around the Earth and being directed to the poles. The stronger the solar wind, like during a solar flare, for instance, puts pressure on the magnetic fields and allows the northern or southern lights to be seen at lower latitudes. But that's more rare. So if you live in Norway, the northern lights are common, or Alaska, the northern lights are a common occurrence. If you live in Wisconsin, every once in a while, a few times a year, you might be able to see the northern lights. If you live in Florida, you're not going to see the northern lights. Now, there are areas in the magnetic field where charged particles can get trapped, and these are called the Van Allen belts. These Van Allen belts are areas of intense radiation, intense, high density of charged particles, very excited particles that are trapped around the Earth. So when the Apollo astronauts went to the moon, they had to pass through these Van Allen radiation belts. They only spent a few minutes to a few hours in the Van Allen radiation belts as they passed through them. However, staying in the Van Allen radiation belts increases cancer rates significantly. So you would not want to stay in those areas, but if you pass through them quickly, basically the radiation you get is equivalent to a few chest x-rays. So not fatal. Not great, but not fatal. Now, this magnetic confinement we've used in industry. For example, particle accelerators. The Large Particle Accelerator in Fermilab in University of Chicago runs in Illinois. Or CERN, you might have heard of the Large Hadron Collider in Switzerland, or at least part of it is in Switzerland, run by CERN, which is a European consortium of universities and industry. We can accelerate particles to near the speed of light and smash them together by confining them in these magnetic fields. Additionally, fusion reactors, not fission, so not nuclear power plants that we actually have active today, but hopefully the next generation of fusion, where you take hydrogen gas, smash it together to release helium. And we'll talk about that near the end of the semester, nuclear fusion. Hydrogen gas is, when you smash it together at such a high temperature, basically hydrogen gas is just protons. And it's a pool of protons and electrons separated. It's not neutral hydrogen anymore. So those charged hydrogen atoms, since they're charged particles, you can confine them in a space using magnetic fields, which is good because you can't just put that in a container, you're in a metal container, because as soon as that hot gas touches the cool walls of the container, it loses all of its energy. But if you can contain it in a vacuum, in nothing, by holding it there by magnetic fields, it doesn't lose any of its energy. And then finally, mass spectrometers, which we'll talk about, your book talks about in more detail. Mass spectrometers are ways of determining what an object is made out of. So if you get an unknown sample of a poison, or the CSI shows, the procedural dramas, police dramas, will often use a mass spectrometer to determine what the unknown substance was that they found at the crime scene. So mass spectrometers use this idea of magnetic acceleration of charged particles to determine what the object was. Because remember, in the previous equation, the radius depended on the mass of the particle. So more massive particles create larger radii orbits. Smaller mass particles create smaller radii orbits. So you can use that to determine how big or small a particle is, which helps you identify it. So magnetic fields and the application of magnetic fields has a lot of application in industry.